Welcome back. We're going to be doing some more final exam review problems. This one is going to be problem 4 and problem 5 from the review sheet. Let's go. Here's the setup for problem number 4. I have this triangular region where, okay, it's not really a triangle because this edge here is actually the curve y equals ln x, but it's bounded on the left by x equals 1 and on the top by y equals 1. Part A just asks for the area. The area is going to be an integral of the top function, which is y equals 1, and the bottom minus the bottom, which is y equals ln x. As for the bounds, I've already written in here the point where the natural log of x is equal to 1 is at e, so that's the upper limit of my bound. The lower limit is, of course, 1, because that's the x-coordinate where this region starts. So we go about this computation. We first find an antiderivative of 1 minus the natural log of x. For the natural log of x, if you don't know it off the top of your head, you can find it by integration by parts. I happen to know it. And before we evaluate, it's useful to simplify this. This negative x can just turn into a positive x, so I have 2x minus x times the natural log of x, evaluating from 1 to e. And then plugging in, I plug in e and I get 2e minus e times the natural log of e, which is 1. Maybe I'll write the natural log of e here, just for completeness. And then minus, if I plug in 1, I get 2 times 1 minus 1 times the natural log of 1, which is 0. So this term is 0. This term is just equal to e. So here I have, in the first parentheses, I have 2e minus e, which is just e. And then here I have, in the second parentheses, 2 minus 0. So e minus 2 is the final response there. For part B, I'm revolving around the x-axis. So I'm going to draw that in green here. I'm revolving like this. It's tempting to want to use washers here. So in other words, to take my slices like this. But if you do it this way, you'll have to find an integral of the natural log of x squared, which I don't want to do. So instead, I'm going to shift my perspective and instead take slices parallel to the axis of revolution, like this. Meaning I'm going to have to write things in terms of y. I want to rewrite this as x as a function of y, like that. E to the y is the inverse function of the natural log. So if you tilt your head, you see that, well, okay, because we have slices parallel to our axis, when we revolve around the axis, we're going to get shells. So our volume is going to be found using the shells method. The integral I get is the integral. The bounds, remember, everything's in terms of y. So I'm going from 0 to 1 here. And hi, Riley. I'm busy. All right. Well, we're just going to have to live with that. So I'm going from 0 to 1, and the integral is always 2 pi times the radius of each shell. You can see if I'm rotating this segment around the axis, the radius is just the distance from the axis to here, right? This is the point y. So my radius is going to be y. And then the height of each shell is the difference from this curve to this one. So from x equals e to the y to x equals 1. Okay, so sorry, I hope the cat's not too distracting. I'm going to need to expand this a bit. I have 2 pi times the integral from 0 to 1 of y times e to the y minus y. All right, we can solve this integral with integration by parts on this piece. If I do it, I believe I get, and the antiderivative is, we can write it down quickly here, y times e to the y dy. The integral of it is itself y times e to the y minus e to the y plus c. So now if I write down the antiderivatives, I have 2 pi times the antiderivative of the first term, e to the y times e to the y, is y times e to the y minus e to the y. And then the antiderivative of the second term, just y here, is y squared divided by 2. I'm evaluating from 0 to 1. And now I'll quickly plug those values in. When I plug in 1, I get 1 times e to the y minus, so 1 times e to the 1, rather, which is e, minus e, so this is going to be 0. And then I'll have a negative 1/2, so negative 1/2 here, minus, when I plug in 0, so this is what I get from the first parentheses here, when I plug in 1 to the whole thing, I get negative 1/2, and when I plug in 0, I get 0 times e to the y minus, so 0 times e to the 0 is 0, minus e to the 0, which is 1, so I have a negative 1 minus 0. So minus negative 1. So inside the parentheses, I have negative 1/2 minus 1, or minus negative 1, that's positive 1/2 times 2 pi. So the final answer is just pi. So for the last part, we're revolving around the line x equals 1 and finding the volume. So I've chosen to revolve to find the volume using the disk method, meaning I'm going to take the slices perpendicular to the axis of revolution. The reason I'm doing that is because I know ahead of time that it'll give me a better looking integral, but you're welcome to try out the other one yourself and see how it goes. So notice that if I revolve this segment at a height y, say, above the x-axis, or maybe we should say a height y, or distance y along this segment here, I get a disk, and the radius of the disk is the distance from here, which is e minus y, to here, which is 1. So I get the volume is going to be the integral from y equals 0 to y equals 1 of, I have e to the y minus 1 squared times pi, of course, dy. Okay, so to find this integral, I'll first expand. I can take the pi outside. I have e to the 2y, which is e to the y all squared, minus 2 times e to the y times 1 plus 1 if I expand. And then for my antiderivative, I have pi times an integral of e to the 2y is 1/2 e to the 2y. Then for 2e to the y, it is its own antiderivative. I just have 2e to the y. And then the antiderivative of 1 with respect to y is just y. And I'm evaluating from 0 to 1. Now I plug in, I have pi times a big parentheses. When I plug in 1, I get 1/2 times e squared minus 2e plus 1. And then when I plug in 0, I get 1/2 times 1 minus 2, which is 2 times e to the 0, and then plus 0. So this simplifies to pi. The coefficient on e squared is 1/2. I have minus 2e, and then there's a plus 1 here, and then there's a minus negative 3/2. So 1 plus 3/2 is plus 5/2. And there we go. Okay, here's problem 5. I have the curve y equals negative the natural log of x, so it looks like the regular log function, but it's flipped vertically. And it bounds a region with the y-axis here, the x-axis here, and the curve itself, so I get this infinite region, right? It extends infinitely upwards. And the problem is I'm revolving this region about the x-axis. So this is similar to the previous problem in that I don't want to take slices like this, or vertical slices in terms of x, because then I'll end up integrating the natural log of x squared, which I just don't want to do. It's possible, but I'd rather not. Instead, I'd rather switch perspective and take slices parallel to this axis. So I'm going to be using the shell method. because when I revolve this horizontal segment around the axis, I get a cylindrical shell. And to do that, this means I'm going to rewrite this curve, or this function, or I should say, I'm going to rewrite this equation as x in terms of y again. So I get x equals e to the negative y. So that describes this curve as a function of y. The volume then is an integral with respect to y. I'm starting at y equals 0, which is the x-axis, and I'm going to infinity vertically. So I'm going from 0 to infinity. I have pi times the radius, or sorry, it's shells, so I'm doing 2 pi times the radius of each shell is y, and then I have e to the negative y as the height of each shell, dy. Okay, so this goes very similarly to the previous problem, except that it's an improper integral. I have infinity in my upper limit, so I need to turn this into a limit as, say, r goes to infinity, the integral from 0 to r of the same thing, 2 pi y times e to the negative y dy. Off to the side, we would probably want to solve just by itself the antiderivative of y times e to the negative y dy. As before, you just do this with integration by parts. You get y times e to the negative y minus, actually I think there's a minus sign here, minus e to the negative y. Let me check that. Alright, so we have this antiderivative, which you could find on your own, and, whoops, I have the limit, actually I should write it over here, the limit as r goes to infinity, the antiderivative is 2 pi times, I can actually write this a little bit better, you can put the minus sign outside, pull out the minus sign, pull out an e to the negative y, and then I'm left with y plus 1. And I'm evaluating from y equals 0 to r. Alright, I still have the limit here. Remember, you write the limit for every expression until you actually evaluate the limit. So I'll end up with negative 2 pi. When I plug in r, I get e to the minus r times r plus 1. And when I plug in 0, I get e to the minus 0, which is 1, times 0 plus 1, which is 1. Okay, so now the problem is one of determining the limit of e to the minus r times r plus 1. So you can write this, you're interested in the limit as r goes to infinity of, you can write e to the minus r in the denominator, so I have just r plus 1 over e to the r. And you find that this is 0 either just by knowing that e to the r grows much faster than r plus 1, or explicitly you can do L'Hopital's rule to find that limit. So this term goes to 0, and I'm left with negative 2 pi times negative 1, and so I just get 2 pi. So that will conclude this installation of this series of solutions. I'll see you next time.